I will present a work that I did with Yitao recently, and we submitted this to Artificial Life. So it's about NCAs and what NCAs can do for generating textures. I will just summarize what NCA is. So it's a cellular automata. Vasilis talked about it, but the flavor that Vasilis introduced was using NCAs to grow shapes. But the kind that I'm working on is a bit similar to reaction diffusion. So we don't want to grow shapes, but we want to grow patterns which are more homogeneous. So we start from an initial state and we apply NCA update rule, um, which I will explain how it is, and then we get a pattern. And since the update rule of NCA is differentiable, we can have a loss function and a target image to supervise the parameter, to basically guide the parameters of NCA to generate the pattern we want. Um, Now, if you look at the update rule of NCA, it's a kind of residual update. So to get the next state, we have the previous state, and the NCA basically adds some value to the current state to get the next state. Now, this is very similar to an Euler integration of a ordinary differential equation. So in that sense, this will be the derivative of our state with respect to time, and the integration is solved with delta t of 1. This is how NCA is trained. So the NCA is trained using this delta t. Now a question is, what happens if we use smaller delta t's after the model is trained? So here we have two targets, like we train an NCA for this and a different NCA for this. And this is how the train results look. So if we run the NCA, it will generate videos like this with delta t of 1.
So you add the stuff, you start with like always the same.
That's a good question. I will come back to it, but the start is 0. Everything is 0. Um, so it looks fine for delta t of 1, but now we can test it with a smaller delta t. So if the NCA actually learned a continuous dynamics, it should work because um, no matter what the delta t is, we're just integrating over the same thing, and the model should work for delta t even in the limit to 0. But what we see is that for this checkerboard thing, the delta t of 0.1 is working, but for the bubble thing, it's not working. It's just giving us a background state and no bubbles appearing. So basically, all of this presentation is to investigate why this happens and how to solve it. So I will give a summary of how NCA works and what is the architecture. It's a cellular automata, so everything depends on neighborhood. So let this notation like S dot be the neighboring cells of a center cell application X, Y, and T. So S dot is basically R33 by C. And C is the dimension of each cell state. Now NCA's update has two stages. First stage we call it perception. So this neighborhood state goes through convolution, and we specifically use 4 fixed convolution kernels that are not optimized. So first one is identity, which is pretty simple, and the others are some sort of derivative filters. So we have Sobols, which is similar to X derivative, Sobol Y, and Laplacian, which is somehow the second derivative. After this neighborhood states go through this stepwise convolution, we just get one value. So this is how the center cell perceives its neighborhood, and its shape is its dimension is 4 times C. So here we had C, and then we applied 4 kernels, so that's why we have 4C, and we have this expansion of 4 times. Now, this is the only information that the cell can get from its neighborhood. This is its perception. And the rest, the cell doesn't see its neighborhood. So this perception goes through a series of matrix multiplications, and that gives us how much the cell state should be updated. So the parameters of NCA are relatively simple. We have one matrix, one bias, and another matrix. So the first matrix takes us from 4C to D dimension, and then we add the bias in D dimension. We have a nonlinearity, and then we go back from D to C. So, and we get this delta S. And this delta S is finally added to the state of the center cell.
So what is like this outer product like an exponent of S to the left is S, we have S.
Here?
Yes, what
So this is a notation. So this refers to all the neighboring state of a center cell which is located at xy and at
okay.
20.
Okay.
So this thing has this dimension. It's basically this cube. And now, well, this thing happens for all the cells, and we have an update rule of this form. But there is a trick for NCAs that people use for textures, and that's this thing delta here. Why is it low resolution? Anyways, there is, so to mimic biological cells, the authors who proposed NCA added this stochastic update mask. So their intuition is that when you have actual cells, they don't have a synchronizing clock, so they are not all updated at the same time. So what they do is that they apply this mask to delta S, so each cell has a 50% chance to be updated in the next state. And this is essentially what breaks the symmetry between cells, because the starting state, as you asked, is 0 for all the cells. So if we start from this and we don't have this stochastic update mask, all the cells will have the same update. But with this, the symmetry can break. So to summarize this, starting state is 0, and imagine this is the, like this 2D thing that I draw represent the state of whole NCA. So each point that I draw here is in this is in a very high dimensional space that represents the state of whole NCA. So since the starting state is 0, everything starts from the origin, and then NCA gives us the update. So we take these updates given the parameters, and we have this sort of evolution. Now another NCA can have a different parameter, and it gives us this evolution. Now this is delta t of 1 and how it's trained. And actually, if you run this again, because of that stochasticity, it will take a different path, but they're all somehow near each other. So now what happens if we test it with a smaller delta t? So that's like taking smaller steps. And for this checkerboard one, we saw that it goes nearly to the same places. But for this bubble, it starts and then it somehow diverges to a different place than what we want. So you might ask, what's up with this checkerboard and bubble, and like which patterns are in which, like what happens for each pattern? What we find is we find that there are kind of two groups. Like group B, if you run and save with the small delta t's, it's fine. It can create the correct pattern. But for group A, when you run it with a small delta t, it just converges to a uniform state, which is kind of like the background color of the pattern that we have. I'm not quite sure about this, but my hypothesis is that this is somehow related to solitons. If there are solitons in the pattern, the NCA needs is not continuous. Actually, it needs that discrete. It just works with the time step discretization that it saw during training. So to understand why this happens, we can have two different. Uh, we can I'm gonna show what happens if we use different schedulers for delta t. So first scheduler is this. We start with delta t of 1, which is the one observed during training. And we use this delta t until time is less than the critical time. And after critical time, we use a small delta t. So how this is that first we take larger steps, and after some time, we start taking small steps. And the other scheduler is opposite of this. So we start with small delta t, and then we take larger steps. So this one is like smaller steps, and then larger steps. So we can see what is the output of NCA for each of this. And the funny thing is that for the one that we started taking large steps, it's fine, it can create the correct patterns. But for the one that starts with small steps, it can't. It gives you the background. So what this tells us is that this sensitivity to delta t is pronounced near the origin. So the model somehow uses the large delta t to like kick out of the comfort zone near the origin and then create the pattern. So here in this figure, we show the results when we vary the critical time. So as you can see, if you increase the critical time, like you set the critical time to 8, the scheduler A works. So it means that the NCA needs to have large steps at least up to time like 6 or 8. And what the second row shows is that if you didn't take any large steps in the beginning, after that NCA fails. So if you take small steps in the beginning, then no matter how many large steps after that you will take, the patterns will not be created. So how can we fix this? We found a small, simple solution that fixes this, is to just change the initial state with noise instead of 0. And this makes a bit of sense because we saw that the model is especially sensitive near the origin, which is its starting point. How much time do I have?
You can have like 8 minutes still, if you want.
So we set the starting state to uniform noise. And then we also remove the stochastic update mask because starting with noise already breaks the symmetry between the cells, so we don't need to have that. This is comparison with the NCA, so you can see that if you start with noise, your model works for small delta t's, but if you don't start with noise, it doesn't work. And this is a quantitative comparison. So we compare the relative quality of NCA output compared to the delta t of 1. So you see they all start from here, but the one that has the stochastic update decays in quality as you decrease delta t.
Where is the PNCA?
So that one is like letting the cells to know their position. So when you do this, this is another kind of symmetry breaking. So they also use that information to maybe get out of the starting point. So up to now, I showed you that NCAs can be continuous in time. So it's actually learning an ordinary differential equation. Now I want to show if NCAs are continuous in space. So of course we do everything in discrete space, but then we can increase the resolution, and that's like simulating the continuous space limit. So I told you that we use frozen convolution kernels that are not trained, and there's a reason for that, because they actually resemble spatial gradients. But to actually go from convolution to gradient, we need to divide the output of the convolution by the pixel size. This is how we estimate gradients with finite difference method. So we have to divide this by 1 over delta x, 1 over delta y, and for the Laplacian, which is second order, it's a bit more complicated. But we have to divide this into two parts. One is second derivative with respect to x, and the other is second derivative with respect to y. And then we divide each one by their corresponding pixel size. But when delta x is equal to delta y, it's easy. It can be this. And there is a trick when we change delta x. So in training, delta x was 1 because delta x delta y are 1. But in test time, we can change delta x and delta y. So if we set delta x to something like 0.5, each of these, so these two will be scaled by 2 and this one will be scaled by 4. So we have to scale down delta t also, because otherwise things will explode. So we set delta t to be minimum of 1 and delta x squared. Now we can simulate the NCA at different resolutions. So this is how training looks like. And then we simulate it on a larger grid, but set the delta x to 1 over 2 and so on. And so this is the noisy one, not the NoiseNCA, not the one that has a stochastic math. So again, you see, compared to the normal NCA, it works much better. And here you see the relative quality in the limit when we make delta x smaller and smaller. And as you can see, this is not as good as the time version, because in the time version we had much higher relative quality, but here it decays much more. So what can we do with this is we can somehow create multi-scale patterns. So here we have a very large grid, but each pixel has its own delta x. So here we have very low delta x, and then it increases and then it decreases again. And what happens is that this allows you to create some sort of multi-scale patterns. And then you can also use different delta x and delta y. So this will create anisotropic patterns. The labels are wrong, but so decreasing delta x is like stretching horizontally, and decreasing delta y is like stretching vertically. The other interesting thing is that you can play with delta x and delta y over time. So here I'm decreasing delta x, so they get bigger. And this is quite interesting. Like here you can see that the solitons can preserve themselves, and then when you increase delta x, they somehow divide into two, which is an interesting behavior. You can go here also, like in this link, and maybe I can show it quickly. So it's NoiseNCA, and it's a GitHub page, .github.io, and you can play with these models here. So here you can, it doesn't show. Okay. So here you can choose the pattern that you want, and I can. So this shows how many steps per second we take. Then we have delta t, and when delta t is small, you can see how you can see continuous appearance of the patterns. This is a bit this is something very interesting, and the other one is to play with the scales. Yeah. So you see, it's not quite robust. Now that I increased delta x, there are empty spaces. But if I start like this, there is no empty space. So the model can still be improved. I have a few more things to show, but it's near the end. So there is also another interesting thing that can be analyzed here. Vasilis introduced the concept of quiescent state. So quiescent state is a state in CAs that if you have a neighborhood which are all in that state, they're stable, so the center cell won't change. And for game of life, the white thing is the quiescent state. So now we can we can basically study the concept of quiescent state for NCAs. So if if we want to find a quiescent state, we should consider that all of the cells in the neighborhood are in the quiescent state. So yeah, basically all of these will be the same. And then if they are all the same, if you apply Sobol and Laplacian, it's zero. So they don't have gradients. So if you look at their perception vector, which has 4 components for each of these filters, the part for the Sobol and Laplacian is 0. So their perception vector is just ZID, which is the state of the center cell. And then if we look more carefully at the matrices which store the weights of the NCA, the W1 has 4 parts, so W1 ID will be multiplied by this, W1 X will be multiplied by this. And since these 3 parts of the perception vector are 0, we only need to consider W1 ID. And the perception, the ZID will be the state of the center cell, which we wanted to be the quiescent state. So if we write all of this, we can have an optimization problem to find this quiescent state. So in the quiescent state, we ideally want deltas to be very small, 0. So we can write this like as an L1 or L2 norm, and we want to find a state that this is minimized.
Should try to wrap up.
Yeah. I need 1 or 2 more minutes.
That's fine.
So I showed you that for textures like this, we go to back something like this, the NC output is like this. But for the other one, the NC output is fine. So now we can solve the optimization problem that I showed before to find the quiescent state. And we see that actually the solution to that optimization problem is the same as what NCA converges to. So it means that when delta t is small, NCA converges to the quiescent state. But for textures in group A only. Now we know that PDEs are reversible except in the fixed points. ODs and PDEs are reversible except in the fixed point. So if we start from here and we follow the updates of a PDE, we go from here to here. And if none of them are fixed points, we can do the same and it will go back. Yeah, but this won't happen in fixed points because in fixed point there are many arrows that go inside. So is NCA reversible or not? So here I'm showing running NCA in forward mode, and here it's in the backward mode. So I just apply the minus of the update. And what you can see is that in forward mode it's fine, but in backward mode it starts to mess up in these regions. So this is another proof that those regions are the fixed point state of the NCA. Yeah. And if you run it more, it's completely diverges, but yeah, as you can see, the divergence starts at those fixed points. Yeah, that's all. Thanks.
Questions?
Yes. So, can you characterize the region where goes to this quiescent state or not? Because so it was depending on the patterns on the images or something. So have you more intuition into that? Did you try to characterize how big is this region? Or
I see. I have no idea about its size. I mean, but so I can give you some time scales. The patterns appear around time of 100. So yeah, like they're almost complete around time of 100. and you need to take large steps up to time of 4. So it's a very small time scale compared to the time that patterns appear, and you actually don't see the difference in the beginning. In the beginning, with the small time steps and large time steps, visually they look similar, but one of them doesn't create the bubbles.
Did you try visualizing also the hidden channels in these
They
beginning
look
moments?
they look pretty much the same. I mean, it's just looking at it in a different color space.
Okay. I have a question. So I was wondering, did you try training some NCAs with a smaller delta T
So
to
that's
see if there is some delta T
yes.
value where you become continuous in some way?
So yes, I tried that. Let me
Okay.
go back. So the bubble one doesn't work with 0.1, so you can train it with 0.1.
Yes.
It's a bit tricky to train it with 0.1 because then you need to take more steps.
Of course, yeah.
And you have memory issues and gradient explosion and blah blah.
Okay.
But yeah, if you train it with 0.1 and you try so hard, it can work with 0.1.
Yeah.
But it doesn't work for 0.01.
Okay, that's what I was wondering.
So like you can push it back, and what it might does is that it might scale its weight so they produce a larger output. But there is really a singularity there.
Okay. Yeah, I was wondering about, so in the examples where you put the noisy, so again, I'm not very good about this kind of Brownian motion stuff. I don't know much about, but somehow the stochastic update, it's kind of strange as you take delta t to 0, right?
Yes, that's true.
So I don't know how to control that. So is that why you removed it for your?
I removed it because it messes up with, like, it decreases the quality when you start from noise.
Okay.
But anyways, like, yeah, I think in case you have stochastic update, the continuous limit is a bit vague.
Yeah.
Things I've tried is like making delta t to also be a random variable instead of like 0 or instead of 1 or 0, it's like in between. But it doesn't work. I mean, it's not the problem.
Yeah, so one last thing I was wondering, so you say that this continuity of the NCA depends on if there are solitons or not.
Yeah.
Could it be that it's rather than solitons, at least in the example you've shown, seems that the size of the feature, the size of coherence that your NCA must generate is bigger in the case where it fails to become continuous. So what I mean is that the bubbles are bigger than the checkerboard size.
I see.
And kind of the big squares are much bigger than. So could it be related to kind of the size of the features that you need to learn instead of whether it's solitons or not?
Let me double check.
Yeah.
I don't think. So for example, for this one, this, you see, this one is, I would say is very large. It's like these squares.
Right.
But this one is continuous, even the normalization.
I see. So you need to have some sort of empty space between the solitons. That's how you define soliton, is that it's surrounded by some sort of empty space or kind of background.
Like there are discrete things traveling, and then there is like something like a background that separates them.
That's quite interesting because it's interesting to see, for example, for Lenya as well, because Lenya is also this thing that in principle it's not really continuous when you take dt to 0. And would it be also related if you take two Lenya parameters, one which doesn't have solitons and one which does have?
I see.
Does this still apply? So is it a reliable way to kind of detect solitons in these pseudo-continuous systems? It's very, very interesting. Okay, thank you.